Thank you for inviting me, first of all, and thank you all for being here. And I know that we all are so very busy, and to find time to attend these events is difficult. But I'm delighted to see you all, so many people in the participants list. And when I was first approached by the super ladies who are organizing these events, and they said, Carmen, can you tell us what you guys are doing at the in your program grant about how can electronic devices or systems evolve digital manufacturing? I had to say yes, because a lot of the work that we are doing, that we are going to do as part of our Reimagining Engineering Design program grant has to do with that. And I wanted to give it a spin of we are engineers who are trying to do digital manufacturing as part of re-engineering design. And we have engineering designs that are very much wanted, because we do need them to evolve our digital manufacturing scenarios and approaches. I want to start with sharing this screen, which shows who we are. We are 3 universities. It's led by Queen's, and Loughborough and York are also part of the academic team, and a long list of industrial partners that are coming with us in this journey to reimagine engineering from a cyber-physical, social, natural inspired evolution process. And I'll speak about that a little bit. I have seen the participants list, some of the people there are members of this, of the team, of my team. So special hi to them. Thank you for being here today. And very quickly, before I give you a couple of examples of how we are gonna need, or how we are going to expect from the sensor makers and the electronic system designers and makers for our digital manufacturing needs. Very quickly, first of all, I want to explain to you what the work from a bird view point distance, what it is about. So we've got 4 threads. One of them is the design theory that weaves everything together and carries modeling, design, manufacture, as well as the physical validation concept to reality, in order to have the design that is goes hand in hand with manufacturing processes that will have to be novel to be able to design those new things that we want, new designs, new products, new systems, new services that we want to develop through that, and eventually embedding everything in the extended manufacturing enterprise, not forgetting we are going to have humans in the loop. So that's an overall picture of what we're doing, really up there, bird view, as I say. But what I brought you today is 2 examples of how we are going to need electronic systems, electronic devices, to evolve the digital manufacturing that we have in mind, to re-engineer design in the manufacturing world. So the first example I bring you is work that we're doing in my lab around composites manufacturing, and why we need electronic devices to assist that manufacturing. And then the second example, the second case study that I bring you is work that we've continue doing, and will do as part of this program grant as well, on automotive assembly lines in automotive industry. The where is my engine? And I'll touch on that in a few minutes. So first example is on the manufacture of composites. Composites, you have a matrix, typically a polymer, then you have a reinforcement, typically a fiber, carbon fiber. And when we make those, we encounter lots of challenges and lots of problems. So I want to talk to you about the pixel-based heating approach to manipulate Cure-induced defect and distortion. So just to set the scene, transport industry, although this could also be applied to automotive, to cars, etc. Okay, sorry, I heard somebody say something. Was that to me? No?
No, I think maybe someone just unmuted accidentally.
No problem, no problem. So we've got an aircraft, for example. The blue areas there is where composites are. So as you can see, a large proportion of the body of the aircraft is going to be composites. Now, and then on your right-hand side panel, you've got typical parts of an aircraft that are made out of composites. Sort of composites that we are talking about today, that we are dealing with. Those plastic matrices, the polymeric matrices reinforced with carbon fiber. The first speaker was also talking about maritime, and composites are also used there. So this is for you to have a picture of what we're talking about. The way they're made is quite rudimentary and has not changed very much in the last 50 years. So you lay up layer by layer. You put your plastic, and you put your fiber, and your plastic, your fiber, etc. You cure it, and then you machine it. You make it into the shape that you want. Now, when the curing happens, things can go pear-shaped big time, and you can find defects. You can have defects and cracks and delamination, and the whole panel can be warped and deformed. That not only is a problem to security and safety, in particular if you're flying in that box, but also is going to throw your design plan out of the window, because things are not going to fit anymore. Things are not going to do the job that they were intended to. So one of the things that we are working in my lab, and Shotin Liu, one of my students, is working in, is in creating new manufacturing processes for controlling the curing process, so we avoid those points of deformation, warping, cracks, etc. So I don't want to spend too much time talking about this, because the point I'm trying to make here is the next slide, which is that we need to control where we put the heating spot on that panel. And there needs to be a way of sensing in a very harsh environment, very high temperatures, and a lot of fluid mechanics and multi-physics going on there. Sensors that we can interrogate, we can get information from, and then react to that, and a control loop to go back in order to manage and balance that heating profile across the entire polymer. So a new manufacturing process for solving a challenge in a well-established industry, however, doesn't have the sensors that we need for that, because there are no sensors that can, this moment in time, that can survive in these conditions and that can allow us to do that control. So we are creating the manufacturing process, and at the same time, we will have to create new sensors that are suited, that are up to that challenge. So that's one of the needs that we've got in terms of instead of having electronic devices and electronic sensors and control systems that allow us to realize the manufacturing process that we have thought up and dreamed of in our heads. So that's one. That's the first example that I bring you as I say, as the need for electronic devices to help us in our manufacturing journey. The second one that I wanted to show you today, another example, different, is in the automotive industry, in the assembly line in automotive industry. And we have to remember that even though the sonky pictures that we see in the news or in the magazines are all done with robots, there's still a lot of human intervention, a lot of humans being involved in those assembly lines. So first of all, where is my engine? You speak to multinational, I don't want to give the names of the people we work with, but big names. Most of you are driving one of their cars, and they go into their factory, and surprisingly for us, you would think they have everything well controlled. They go, oh, where is my engine? Where is my engine? Where is it? We have a warehouse full of metal parts, not just the racks, but also the engine itself, a metal block of thing. And people would say, well, you just need to connect an RFID tag on it, and you can watch it move within the warehouse and through the assembly line. Well, it's not as simple as that, because as I say, we're going to have lots of metal that create what is we understand as a Faraday cage. Things moving at high speed in those forklifts, and those forklifts are driven by people who have a different behavior at day, at night, etc. I'll speak a little bit about that. So not as simple as attaching an RFID tag in that, again, a harsh environment for different reasons. Harsh environment, the previous example, was because of the high temperatures and pressures. Now it's a harsh environment because of the electromagnetic field that stops us from reading that, from communicating with that RFID tag. It's also moving at high speed and high accelerations, where it's being taking places with this forklift. And we must not forget that, as I said, there is a human in the loop here, and the human component that needs to be considered for this challenge. Now, let me talk a little bit about this person who is there kitting this engine. This person there works, or is paid by the number of engines that she pushes through the assembly line. It's not paid by the number of engines that make into the car, i.e. successful engines that make it into the car. It's not paid by the hour. It's paid by the number of engines that she receives, processes, and pushes forward down the line. So if an engine arrives and it's got the wrong barcode or the wrong RFID card that doesn't read or has fallen off, this person who needs to kit it, scan it, and move it on, stops and thinks, right, okay, I am wasting time here. I don't know what this engine is or where it should go. So they have to make decisions under a lot of pressure, time pressure, and knowing that the time is ticking and that another engine is coming down the line, and this engine is not being pushed down. So they are tempted to or fall into the temptation of making decisions for themselves. And those decisions, in more cases than we would like, is the wrong decision. For example, we've got here, the blue pieces are pieces that look scarcely alike when you have them in your hand. However, they're all different because they've got different tolerances. We're talking about 47, 63 microns holes. Okay? So when either the RFID tag or the barcode is not there, is not present, or is wrong, the human has to take the decision of which one to use, and may put it in the wrong engine, or may, as I said, put it in on the wrong tray, as we've got here, that's moving along the assembly line. And what happens when the wrong decision is made is that these engines have to be scrapped, have to be put in the engine graveyard. As you can imagine, is millions and millions and millions of pounds worth every month. So electronic devices are needed for harsh environments, i.e. heat or electromagnetic fields or high-speed accelerations. We need, this is almost like a wish list that I've created, reflecting on these two examples that I brought you. As I say, they need to be able to operate in harsh environments. They need to be able to give us the information to manage high variability in production lines. In production lines, you were talking earlier about the food industry. That's another great example of this. An assembly line, a production line is producing different products simultaneously. So the user or the person who's the operator needs to deal with that high variability in the production line. Needs to enable decision making, both via data analytics. I mean, the amount of information that is there in time, information in time, accurate information in time, easily read, but also the quality of the data. For example, we're working on chips that do process that with a partitioning that's processing on the chip directly. So instead of receiving all the raw data from the sensor, we are receiving data that's already filtered, which makes it much easier for in terms of computational power where we are. And this is an obvious one, isn't it? Reducing waste and wasted resources, not only time, but also, of course, wasted materials, because we all need to start breathing and sipping into the circular economy. Right? The world is a lovely place that needs to be looked after. In terms of control stock and assembly line monitoring, what I said earlier, where is my engine? It doesn't go missing, it doesn't go mishandled, doesn't end up in the graveyard. And also the importance of speaking to the sensor in time and on time. In the current majority of process and production stages, we are measuring many meters down the line, or many minutes down the line in the assembly line, when the mistake has already been made. And sometimes it's just impossible to go backwards. Therefore, that wastage, because it's in a way cheaper to discard a faulty item, engine or composite panel, rather than bring it back into step one. Sometimes it's just impossible. The composites, for example, it's just very difficult to undo them as such, right, and put them back. The human in the loop. We do need to design and plan sensors and electronic systems that do take into account the human in the loop, as the assembly line kitting errors that I just spoke in the automotive industry. And there's an important aspect of all these that we engineers perhaps are not immediately going to think about that, which is the ethics behind sensors. If we put a sensor that measures everything that is happening in an assembly line, in a production line where humans are involved, we are going to have some issues to deal with on how those humans are perceiving how we are watching that assembly line. And typically humans don't want to be watched so tightly. It's the big brother effect, isn't it? Humans don't want you to know when they're going to go for a tea break, or when they are going to, how many hours they're spending at their post. And we have discovered through the years and through this work that people don't really do what they tell you they do. And by the introduction of sensor systems and electronic systems that monitor the process where the human is involved, there's going to be an aspect of psychology and as I say, resistance to moving forward, advancement and innovation that we also have to deal with. Because if the human in the loop, if the operator doesn't want to use a piece of kit that you have designed for them to improve their process in their manufacturing, it's just not going to happen. So we can become really clever at designing new technologies and new electronic systems, but if the end user doesn't put it into action, it's really not going to work. So an aspect of social engineering there that we also have to take into account. And this was really a very quick show, a very quick pit stop through what we are doing in REAR, in the re-engineering design or reimagining engineering design with manufacturing and of course digital manufacturing is almost a given, and how we need electronic devices to assist us and to help us evolve digital manufacturing. Thank you.